In today's class, we are going to talk about the demodulation of an FM signal, or for that sake, a PM signal. Before moving on towards the demodulation of FM or PM signals, let us recall how we generated a frequency modulated signal using a Simulink. So Gfm of t is equal to A cos of omega ct, the carrier frequency, plus kf, the sensitivity parameter, and integration of m of alpha, which is basically in our case this signal m of t. So it's integrating from minus infinity to t, and then our argument of the cos function is closing. So this whole expression is basically implemented over here in the Simulink. Starting with the message signal, so I have considered a simple sinusoid. This is a sine function. I have set the amplitude equal to 1. This is simply 2 radians per second, and I have set sampling time equal to 0.001. Note that these blocks can be obtained from library browser, right? So this is our message signal, and then we have kf, that is the sensitivity parameter. So this is represented in terms of a gain block, and I have set the value of that equal to 10. Okay, so note that this is not kf, this is kf by 2 pi. So kf by 2 pi is equal to 10. Next, what we have is we have a carrier frequency. So what I express over here is in terms of hertz, that is fc rather than omega c. I set it to 20. So message signal was at low frequency at 2 radians per second, while the carrier frequency is at a high frequency, that is at 20 hertz or 40 pi radians per second, right? So then we have a summation block here. So that summation block is expressed over here. So all of these three blocks then multiplies with another gain which I have mentioned as 2 pi. So this 2 pi will multiply with fc, so this will become omega c, and similarly kf by 2 pi, there's a 2 division by 2 pi over here, so this would multiply with this 2 pi, and eventually you will get kf, and then the message signal would be just simply represented over here, right? Now this block would be then passed through an integrator. So if it passes through an integrator, the fc into 2 pi, that is omega c, would be converted to omega ct, while for the rest you would have kf and the integration block, because the message is dependent on time. This was constant, this was independent of time, but the message signal is dependent on time, so we have an integration appearing over here. All of this is basically fed into a cos function which I have expressed over here. Also note that I have used a discrete time integrator, but you can also use, or preferably that you use a continuous time integrator. For a later work, I have considered just discrete time integrator in this simulation, and eventually then we would pass it through a gain which is just unity, so it will not play any role over here, and the output of this is fed to a scope. At the same time, message signal is also fed to a scope. Also, the message signal is fed to spectrum analyzer, and the frequency modulated signal, this is the output is the frequency modulated signal, so this is also fed to the scope. So if we simulate it, right, so we have a time domain signal over here, and this is our message signal, the upper plot in time domain, and this is frequency modulated signal. So let us zoom on the x-axis, say until here. So whenever the amplitude is high, the instantaneous frequency will be higher. When it is low, it would be lower. So this is reminiscent of a frequency modulated signal. Now in terms of spectrum, we have, let me again zoom this one. So let's take it until minus 50 dBm. Remember, dBm is simply 30 plus log 10 of W. W is just watts. So we have two curves over here. The first one is this golden curve. So this golden curve is appearing from our message signal, which is a baseband signal. So it's called baseband because it is centered at zero frequency. This is a low frequency signal. And then we have an output of a frequency modulator, which is appearing over here in this blue line. Note that the blue line is roughly centered around 20. So this is the carrier frequency that we set, right? Now consider the bandwidth of this one, the bandwidth of the passband signal, the blue one. So the bandwidth of the passband signal is roughly it is actually by definition the maximum frequency minus the minimum frequency. So over here we have roughly around maybe 28 hertz. See, you can remove this section and you can remove this section, so roughly around 28 hertz. And the bandwidth of the baseband signal is generally this bandwidth divided by 2. So if you divide this by 2, so you would have around 14 hertz, which is over here. So 14 hertz means it is going to start at 0. Bandwidth is just for the positive frequencies, so it is going to start at 0 and it would terminate at, right. In the context of demodulation of FM or PM signals, there are several methods that can be used. First and foremost, we would look into the conversion of information from frequency or phase to amplitude, so that all the techniques that we have used in the demodulation of AM signals can be replicated over here. Specifically, we have two such methods which do this conversion. The first one is signal differentiation method. Another one is frequency discrimination method. We also have a phase lock loop, and moreover there are other methods such as balanced zero crossing FM detection. In zero crossing, you count the number of times a given signal crosses 0, right? Presently our focus is on these two methods. So in the conversion methods, what we know for sure is the information of baseband signal, that is the message signal, is contained in the frequency of FM signal. So by that what we mean is that the message signal or the information is contained inside the frequency or generally the phase of a signal, of a frequency modulated signal. So this information we are given with. What the requirement is for this method, we actually need a circuit that can detect the message signal m of t from this waveform gfm of t. The circuit needs to be simple and inexpensive. In our previous discussions, we have mentioned that the simplest circuit is an envelope detector. This is an envelope detector. So the incoming signal that passes through a diode, and then you have a capacitor and a resistor, and on top of it over here you also have a series capacitor that blocks DC. But this is a fairly simple circuit. So the requirement is to somehow use simple circuits to recover back the message signal m of t. The problem is the envelope detector, what it does is it tries to detect the amplitude only, not the phase. So this would lead us to some techniques in which we can convert this phase to an amplitude. So we will look into this aspect next. Just one quick review. In the envelope detector, you have these ripples, and these ripples are basically nothing but RC constants, or usually we call them by a time constant tau. So depending on the values of R and C, you would have this waveforms. So this waveform is, what is this representing? This is representing an incoming signal. So when your incoming signal is above 0, it would charge the capacitor, but once it goes down, the capacitor will discharge, and the voltage again across the resistor would be observed, right? So it would discharge, but the rate of discharge would be much slower than the frequency of the incoming signal. So in the next cycle again it will charge, discharge, charge, discharge, and so on. So we have to be careful in the design of R and C. If it is too small, then what it would do is it would just go down, be 0 on this point, and then come back up again, and so on. If it is too large, you would have this behavior. So it would not be able to track the message, the incoming modulated signal, right? So this is our motivation, that even though the information is over here, we need to somehow convert it into the amplitude. This is our aim that I have just mentioned. So the solution for that is, if you take the derivative of this signal, of the frequency modulated signal. So by derivative we know that if you take the derivative of cos theta, you would have minus sine theta into the derivative of the angle, right? So from cos it would convert to sine, and you would have a minus here. And if you take the derivative of this term, so omega ct by dt, so the t will would cancel off, and you would simply have omega c over here. Kf, the sensitivity parameter, would retain itself, and differentiation followed by an integration would cancel with each other, and you would simply have a message signal over here, right? So if you have the incoming frequency modulated signal, you pass it through a differentiator. So this expression is something that you would achieve, because the amplitude now consists of m of t, right? So if the amplitude is time varying, we can go back to the envelope detector, right? And with an appropriate choice of R and C, we can get this behavior, or the upper side with ripples, this waveform. After that, there are some high frequency contents. You can use a low pass filter to remove these, and furthermore you would see there's a DC value over here, right? So to remove the DC value, you would need a DC block, that is a capacitor in series with the circuit, and eventually you will get the message signal m of t. Note that for a differentiator, the transfer function is simply j omega. So if you plot the magnitude spectrum of it, so it is linearly increasing. So what you would have is, you would simply have a straight line in the frequency domain, and this is your carrier frequency omega c. So the amount by which the instantaneous frequency would shift from omega c would be directly proportional to the message signal m of t. We have the differentiator that is used for a slope detection. You're basically detecting a slope. Similarly for PM, again the aim is to use the envelope detector. So what we do is we take the derivative again, right? And if we take the derivative, we would have minus a sine of this and then the differentiation of this argument, which is expressed over here. So we would have dm of t by dt. So if it is gpm of t, that is the phase modulated signal that you receive, you would differentiate it, you would get this expression over here, and after that now the amplitude is varying with respect to time, but the amplitude is a differentiation of the message signal rather than the message signal itself, but either ways the amplitude is varying with respect to the time. So if it is varying, we can use the envelope detector. We can remove the average value or the DC offset. Once we have removed that, we have to uh, we would get back our dm of t by dt, right? We would get this signal, right? So but what we need is we need the message signal. So if we pass it through an integrator, so the differentiation would cancel off with the integration, and then you would get back your message signal m of t. In the frequency discrimination method for the demodulation of FM signals, again the aim is to convert the information from the phase or frequency to amplitude. Previously we have done that using a differentiation block, but right now we need to replace the differentiation block with an appropriate filter, and we again intend to use a slope to achieve m of t from the frequency modulated signal. Hence, to start with, we will have a frequency modulated signal that would pass through an appropriate filter, which I have expressed as h of omega. Previously in the differentiation, that was basically, this was simply h of omega was equivalent to j omega, right? So what this would do is this would generate a time domain signal whose amplitude is varying with respect to the message signal. And once we do that, we would eventually use an envelope detector followed by a DC blocker or simply a capacitor in series with the circuit to achieve back our message signal, right? So what we intend to do is generation, previously mentioned. This was the baseband signal and this was frequency modulated signal. So we need to design a filter such that the transition band of the filter h of omega is linear in the range of in the bandwidth range of the frequency modulated signal. So it has to be linear in this range from here to here. So I have sketched one such filter. So if you sketch this filter, since it's linear, a spectrum that would directly relate with the message signal. How it is done? First, let's look into the model. We have GFM of t, which is our message signal. So we split it into two branches. After splitting, in the first branch, in the upper branch, we have a filter, which is a band pass filter. So this tuned circuit has a behavior as shown over here. From here, starting point, and then terminating point. This is tuned at FC F1, right? Similarly, the other branch, which is over here, is tuned to again a band pass filter, but at a lower frequency. So it is centered at F2, and then we have a similar structure for the band pass signal. So next what we do is we need to get a slope which is linear, as mentioned previously over here. We need this linear slope which is quite extended. So if you invert this and subtract this from the inversion, eventually you will get this plot, right? So once we achieve this slope, now this slope, what it represents is, it just simply represents the variation in frequency with respect to the message signal. So this slope directly relates to the message signal m of t. So once that is achieved, we can proceed on towards envelope detection and just simply addition or deletion of the two signals. So let's look into what is this tuned circuit. The circuit is simply a resistor and an inductor and a capacitor. This is just simply a band pass filter. And similarly, by changing the values of inductor and capacitance, we also have a band pass filter for the second circuit, right? Next, the envelope detector is, as you have seen previously, simply a diode followed by a capacitor and a resistor. So we have the two envelope detectors appearing over here, and finally we have an output which represents our message signal m of t. Again, a fairly simple circuit. So in terms of the Simulink block or the Simulink environment, uh, there is a block which is called FM Demodulator passband. Since this is a passband, so we are demodulating it. So let's look into the simulation environment next. Previously, we have generated the frequency modulated signal. So we would use a demodulator, that is FM demodulator passband, which has a carrier frequency 20 Hz, inconsistent with our original generation, and frequency deviation is simply 10 Hz, which is expressed over here. And then I have set the order of the filter to be 250, right? The output of the frequency modulated signal is fed into the FM demodulator, and the output of the FM demodulator is fed to the scope. Also in the scope we have a frequency modulated signal and the original message signal. In the meanwhile, the output of the frequency modulator is also fed to the spectrum analyzer. So let us run this experiment. So we originally had the baseband signal and the passband signal. So after demodulation, we will get back our original baseband signal, which is centered at 0 frequency. You can observe that we have almost captured the original signal, but we also have some side lobes appearing over here. In ideal situations, this golden curve should be exactly equivalent to this curve. So you may select an appropriate filter to get rid of these side lobes. So in terms of time domain interpretation, this was our message signal, this is the frequency modulated signal, and this is the outcome of frequency discriminator. Let me zoom this on x-axis. So you could see that at low amplitude, at low frequencies, you have these oscillations. So these oscillations actually represent a high frequency content in a recovered signal. And if we go back to the plots, these are the side lobes which are reflecting on the oscillations in demodulated signal. As known, there are several methods for demodulation of FM signals. So previously we have discussed the conversion methods that included signal differentiation and frequency discrimination. Now let us move towards the phased lock loop. In PLLs, we feed the frequency modulated signals and try to obtain the message signal or the information signal from it. PLL is nothing but a feedback control system where the output of the loop filter is fed to a voltage control oscillator. So there are three significant blocks over here in the PLL. The first block is the phase detector, which is simply a multiplier. The next block is the low pass filter, and the output of the low pass filter is fed to a voltage control oscillator. And what VCO does is if it produces an instantaneous frequency which is changed based on the input voltage. Now let us consider our generic signal, which is GFM, that is equal to A cos omega ct plus the sensitivity parameter Kf, and then the integration minus infinity to t m of alpha d alpha. And we also have an output of the voltage control oscillator. So that would be simply V output of t, that is equivalent to B sine omega ct plus K, the integration of an input signal, and for here the input signal is V2 of t, so V2 of alpha d alpha. Note that there are some parameters which are changed. Initially, the constant amplitude of the modulated signal that a PLL receives is simply A, whereas the constant amplitude that the VCO produces is B. Both A and B are not dependent on time. Moreover, we have a cos function at the input, whereas the output of VCO is giving a sine function. So there must be a phase difference of 90° between the two, which is ensured by means of cos and sine function. The free running frequency, which is omega ct of the VCO, is as per the carrier frequency by means of which we originally modulated the FM signal. Also, instead of the sensitivity parameter Kf, we have a constant gain K, which would depend on the gain of the phase detector as well as the gain of the low pass filter. Right. So these two, GFM of t and V0 of t, are multiplied using a phase detector, and at V1 of t we would have the multiplication of these two, which is A cos theta FM times B sine theta VCO. So if we multiply cos function with sine function, we would have sine of theta FM minus theta VCO plus sine of theta FM plus VCO, which is represented over here. So sine of alpha minus beta and sine of alpha plus beta. Moreover, you would have A times B divided by 2. This is coming from the trigonometric property. So V1 of t is basically carrying two signals. The first signal, you can observe theta FM minus theta VCO. So if you subtract this from this, so omega ct in both of them are consistent, so they will cancel off. So you would have Kf and the integration of message signal minus K and the integration of the output of a low pass filter. So this is expressed over here. This is a low frequency signal because the high frequency is cancelled. Omega c is cancelled. So in the second term, what we would have is we would have 2 omega ct, one from here and one from the VCO. That is 2 omega ct plus Kf and the integration of message signal added with K and the integration of the output of a low pass filter. So this is a high frequency term. So by using a low pass filter, we can reject the high frequency content and we would simply have a low frequency content. So that would be our V2 of t. Note that if the sine function is having a small value, that is theta with respect to sine of theta, so we would have a linear function initially and then it would oscillate. So if the error is very small, the behavior would be linear. So this behavior would track the message signal from the incoming frequency modulated signal. So that's why I have expressed V2 of t, which is related to m of t. So V2 of t, whatever it is, would be fed to the VCO and this would try to track the incoming frequency modulated signal, and then that would be replicated as error, which is V1 of t, and we have a feedback loop system. Also note that there is a certain range around which we would be able to track the message signal from the incoming frequency modulated signal. So we have a pull-in range, that is if the instantaneous frequency of the frequency modulated signal is increasing and it reaches this point, this threshold, so then the PLL would be able to track it and it would be able to track until this point. And once it is in pull-in range or capture range, the instantaneous frequency can either increase and it would still be captured by the PLL, or it could decrease until the hold in range on the left side and it would still be captured. Whereas if the instantaneous frequency is decreasing, so it would have to uh, cross the barrier in the hold in range over here, and then the PLL would be able to track the instantaneous frequency in this region from here to here. Next, we would look into a Simulink environment to have some further insights on the phase lock loop. So in the Simulink environment, previously we have generated a frequency modulated signal using a set of blocks, and then we fed the output of a frequency modulated signal to a demodulator and specifically a discriminator, and then we have observed the detected signal in time domain as well as in the spectrum domain. Right now we are interested in the phase lock loop, and for that the set of um, elements that we would need are represented over here. So starting with the output of a frequency modulator, we feed this output to a matrix multiplier, and this block we have two ports, two inputs. So the first input is coming from the frequency modulated signal, whereas the second input is from the voltage control oscillator, VCO, and for that we have set the amplitude to 1. The free running frequency or the quiescent frequency is 20. This is in accordance with our original frequency of the modulated signal, that is FC, which is 20, and the sensitivity parameter is 10 by 2 pi in accordance with our original gain KF, and then there is initial phase difference of pi by 2. So if we have a cos function here, so we would have a sine function at the instantaneous frequency, which is the output of a VCO, right? Then the third block is a Butterworth filter. This is a low pass filter of order 10, and we have set the pass band edge frequency to be 2 radians per second. This is in accordance with our original message signal m of t. The output of this Butterworth filter would be fed to the VCO, and this voltage would drive the instantaneous frequency at the output of VCO, and hence we would have a feedback mechanism. So in our previous model, this branch was referred to as V1 of t, and this branch at the output of the low pass filter was referred to as V2 of t. So we have mentioned that V2 of t is directly related to the message signal, but due to the gain of phase detector and the low pass filter, we need to amplify it. So we have amplified it by tenfold, right? And the output of this gain or amplifier is then fed to the scope. Also fed to the scope is the frequency modulated signal coming from here and the original message signal. So let us run this experiment. Right. So over here we have a message signal M of t, the frequency modulated signal GFM of t, and the demodulated signal using PLL. So we would observe that initially the phase lock loop would try to track the incoming message signal. At this point you can observe that it is tracking the oscillation, but the amplitude is quite different. So as the samples increase, the amplitude is going to stabilize around +1 and -1 in accordance with our original signal, +1 and -1, right? Moreover, note that this point and this point are exactly matching, and furthermore we do not see any oscillations on the edges of our signal of demodulated signal. Now compare the demodulation using phase lock loop with that of frequency. Over here we have previously shown the oscillations that were present. So this indicates that for the discriminator we would have significant high frequency content still left, but that can be removed using a low pass filter as well. So this also compares our PLL with another technique, that is the frequency discriminator. As bibliography, you may look into these references, specifically Hyken and Moher, for the detailed analysis of phase lock loop. Thank you.